Yeah, so it has to be bigger than number of variables minus 1.
Oh,
Okay, so if you have an 8 by 8 matrix, it has to be 8 at a minimum. That's right.
oh, I see. So that would that affect any like the estimation time, or if
Yeah,
it get really big, or is that?
if it gets really big, then you're going to have a very, very informative prior.
Right.
So if you set it equal to just number of variables minus or one bit, number of variables, and it's the least informative prior that you can make for that data set, roughly.
Okay.
I think it'd be great to make a rating scale where you could. Maybe that's one of the challenges. Has anyone ever published a paper where they've sworn in the paper, or have the F-bomb in the paper?
I get as far as putting being in the title.
Oh, really?
I have a paper that's called How to Life After NHST After No Hypothesis, How to Describe Your Data Without P-IMC.
Oh, that's good. That's a tough one to beat, actually.
I
It's a title.
I didn't come up with the.
That's a title, too.
I didn't come up with the title, but
I was just going to issue that as a challenge.
Huh?
The challenge I'm issuing to everyone here: try to get a cuss word into a paper. See, I think you could do it easily if you had a scale that had that in it, right? Like you can list the items of your scale. That's a pretty easy way of doing that.
So I'm working in a paper that I created the DS index.
Ah, there he goes.
The larger the DS index, the less deterministic recommendations for policy and practice decisions.
I dig it. I have a high BS index.
You have to watch it later.
I will watch it later.
So I was laughing during the missing data conversation.
Oh, yeah?
All my participants no-showed today.
Oh no.
So I was just like, maybe you can keep just all of their data.
That'd be awesome. Let's just make it up.
Yeah.
And that's okay. It's not okay if you fabricate the data, but if you impute it.
Yeah, I'm just gonna estimate it based on their latent class of not showing up.
I think that's a great idea.
Cool.
Yay!
Awesome.
Glad that worked out. Results in 4 hours.
All right, was it a 4-hour run? Did you have a 4-hour run?
I did. My unidimensional IRT model ran, but it took 4 hours.
You're
which
kidding me.
doesn't seem right.
So
I'm still streaming, evidently.
it
Mainly because Ariel's out of the room. Anyone would like to say anything bad about Dr. Aloy? No. Don't say it. Don't say it. I'm joking. Remember, there's no hallowed ground. Would you like me to leave the room so you can say something about that? Of course, I'm recording it, though. I was going to mention, how many of you are still working on homework? Would you like till the end of the weekend? That sound good? Okay. Will that help you get a little bit more sleep? Or a little bit more drunk? I mean, or both. Just make it
Don't drink while sleeping.
Drink while coding. But no, take till the end of the weekend. The reality is I'm not going to have a chance to regrade it this weekend anyway. And by end of the weekend, I mean like 5 to 6 a.m. No, 9 a.m. Monday morning. Okay? Sound good? Are we cool? I just want to make it so you're not stressed. I hate stressing the students out. You are better than stressed. Everybody feel happy now? Okay, but if it comes to Monday and you're like, can I have more time? Oh, no, just kidding. Then stress. No, I don't. I'm fine. I'm way flexible. You all are I know you're trying your best, and these homeworks take an unpredictable amount of time, just like lectures do. Actually, this is part of the reason why I'm pulling my hair out some weeks, and other weeks I'm doing fine. So, are we good with that? Okay. Yeah. Thank you for being honest with me, with telling me you haven't finished your homework yet. That's good. Look what you get for honesty. You get extended time.
It's interesting. I got really weird errors running these models, and they should be easier than CFA. One thing I ran into, maybe other people realize this now.
This is good.
The sampling to get your data set, it samples the student ID as well, which is not a 0-1 variable. So you gotta chop that off before you run your data.
That's right. There's a student ID column, isn't it?
Yeah.
Mhm.
You gotta chop that off. and
Yeah.
otherwise it says,
If you're modeling the student ID, that's probably not going to go well.
child does not match parent.
Yes, that error. Yes, if you give it a variable, this by the way was my problem with the polytomous models when it initialized a 0 probability for one of the categories, the child didn't match the parent.
What is it?
What a great,
It's the most uninformative error.
I tell you what, whenever someone was writing that, they were pretty mad with their toddler.
Right?
Yeah, child does not match parent.
I don't know. R has more vague warnings like you have an error somewhere. Maybe.
Warnings.
Yeah, that's right.
Warnings.
I don't know what it is, but I'm not going to do anything about it. Good luck.
R just keeps saying meh. What does that mean, R?
Now that would be awesome if it had that noise. I rule the world.
Womp womp.
Yeah, that's
Shut up,
right.
computer.
All right, back to mixture models. So the finite mixture model, the way that I'm showing you today, is actually going to be what's called a latent class model. The latent class model has really come to be a very narrow window of finite mixture, meaning you have binary items that have a Bernoulli distribution where you assume the items are independent conditional on the class, right? So you can create one. So given the class of people and items are independent.
Oh, I did want to say one thing.
Yeah.
The mixture model kind of looks like the classical mixture problem from early algebra. Yeah. So you've got you're creating a big container of mixed nuts, and each nut will have some proportion of that mixture and has its own price. And so you ask, if you're mixing these nuts in these proportions at these prices, what should the price of the mixture be?
That's
So
it.
You're doing that, except you don't know the mixtures. Or
That's exactly it.
You don't know what nut goes in where.
That's exactly it. Basically, you forgot to observe the grouping variable in your data. Let your data have a group. Okay.
Do people use it for that?
For what?
Because you scared me for a second.
What are you talking
If
about?
you have,
For
many
what?
times people have a classroom or school level data, but they don't have the ID for the classroom or for the school.
Mhm.
Do people use these techniques to?
Not frequently, although you could. I've hijacked it to do that sometimes.
Okay.
Not for the school level data, but for person level data. You can create, there's all sorts of confirmatory versions of these that are pretty cool, but they function a little bit, if you have a good sense of a lot of data, the training data, if you want to call it that, it becomes effectively like a very interestingly model-based discriminant analysis, because then for each observation you haven't observed, this gives you the likelihood they're in each class, right? You could go look at, if you plug in their data for each class's distribution, you can see how likely it is they're in each class, and you can turn that into a probability based on normalizing it, normalize it. So there are ways that you can use this for your data. In fact, if you think about what we did in the previous class with X and Y, that was sort of going on. We were looking for the posterior distribution of X. It was related to Y given X, right? So that's the class. When X is 0, it's Y given X. When X is 1, times the likelihood of X being 1 or 0. Right? That was sort of what was happening with the multiple imputation already. So there are lots of ways that these models map onto tons of things. There are other really interesting things that you can do with these models, some of which I would advise, some of which I wouldn't advise, and some of which I have no idea. But there's, you've heard of principal components, I know that. There's another version of principal components called independent components.
The what?
Independent components?
Independent?
It's like a Tibbs-Sharani, I believe. Maybe I may be making this.
Don't get that one.
Anyway, basically it's the same idea, but instead of having your components be based on linear algebra with the covariance matrix, it's effectively multivariate normals in the mixture. And so it's an odd, I'm maybe blanking on roughly all of those. Anyway, there's other ways that you can do this. We'll talk a little bit about more of those. But for us today, the data are going to look like this. We're going to have binary data. We're going to stick it in this form. So for within each class, The latent class analysis is a really ridiculously simple and stupid formulation. Basically, for each problem, if you're in class C, the probability you answered the item correct given you're in class C is pi. That's it. What is the one class version of this? The one class version is we're estimating the probability of a correct response for each item. It's an item difficulty in a classical test theory sense. Only here, we're going to do that item difficulty broken down by class. That's the latent class analysis. And you see, this is the Bernoulli distribution right here for each item. You see, each item I. It's conditional on class, so this is f of x given c. And this probability that shows up out front here is the independence function. So once you know a c, we're assuming all items are independent. What could possibly go wrong? Well, where do we see that conditional independence, though? We see it on pretty much every latent variable model, right? Conditional on theta in the IRT model, all items are independent. Conditional on factor in CFA, all observations are independent. Now, there are ways that you can go around that and modify a model to be more general, and the same thing could happen here, but this is the foundation of this. This, Lazarsfeld, Karl Lazarsfeld was, what's his name? Lazarsfeld and Henry is a book that came out the same year that Lord and Novick came out, 68. It's a really good book in a different direction, but it's a very interesting book to look at. So, typically the process, again, would be, I need to first determine how many classes I have. So you fit models of varying numbers of classes. Now you're going to see that this takes a little bit long. So we're not going to do that in class today. In lecture today. But then once you figure out, you fit varying classes, oftentimes you look at information criteria, you say, oh look, the one with the lowest number, that's where it is. In the non-Bayesian sense, there's other tests that you can do. One's called a Low-Mendel-Rubin test to see if another class should be extracted. It's effectively likelihood ratio. I forget it, I don't remember what it is. Anyway, so we're going to pretend that we just know there are 4 classes. And we're going to try to show how this works with 4. This sounds like a really cool idea, right? Oh, let's see how many classes I have. But I will tell you it will break down very quickly and in multiple ways. And so where you can hear me say this version of a mixture model is fraught with difficulty, but there are other versions of them where we can hijack them for good. Not this version, all right? But this is sort of the first pass that everybody comes into it at. About 10, 15, almost 20 years ago, M+ started allowing you to do mixtures in M+. The next thing you know, everybody's like, look, let's see if we can put a mixture on it. Because this model statement, this f of x given c, can be anything. Got a growth model? Growth mixture. Got a regression model? Mixture of regression lines. How would you describe growth mixture for most of the cases?
Stupid right now.
Random intercept. Stupid right now. You heard the stupid right now conversation. That's stupid right now.
It seems like for this to work well, you'd want very few classes that are very obviously disjoint.
Yes, that is what we're hoping to find here. And in binary data, it's very difficult to figure out what that is.
There's like no signal with which to make those decisions.
Exactly. If you have continuous data, it's a little bit easier. But even then, what happens? What ends up happening, I'm just going to give you the fast forward. What ends up happening is if you have the one class model wrong, right? Like for us, it'd be, are items really independent, conditional on class? No. What happens? The only recourse the model has to make the model more right is to extract a whole new class. And that means for us, we have 20 items in our data. Every class that we come about having has 20 more parameters with respect to probabilities, one for each item, conditional on that class, plus one probability for the mixing proportion. So you think about it, model doesn't fit, it's going to throw a truckload more parameters at it. It still doesn't fit, more parameters at it. So what happens in these models, you'll see, there's a guy, was he at Penn State, Nagin?
Yes.
There's
Trash.
there's the proc tragedy. There's a guy doing growth mixtures, advocating.
It wasn't growth, it was just mixtures.
Mixture. I thought it was growth mixture. I thought he had a growth model with it too.
No,
Proc tragedy.
That's a different person.
Never mind then. Well, there were people doing growth mixtures that had advocated for limiting the variance, and I think it was him.
Yeah, he shut off the variance.
You shut off the variance at certain places, right? So basically, making the one class model wrong, which the mixture model would reply by saying, "Oh, this is not right. Let me add more parameters and throw more." So now you get tons of these classes, and then once you have classes, once you have it's just like an EFA. Once you have a solution, you can't unsee it. You're going to make a case for why it's there, right? So these are very easy models to quickly, that are very sensitive to data, right? Well, let me just show you how this works. One of the interesting things with this, by the way, is when we start coding in JAGs, parts of this code are very easy, but parts of this introduce a new distribution. So in JAGs, what we're going to say is we're going to loop across people and items. The data for person and item is deburn, Bernoulli, 0 or 1. And the probability is the parameter in the model, pi. And it's going to be pi of item and then which class a person is. And I put X class there because that helps keep people at the bottom of the output, right? So now, class is our person variable. So when we go down and look at class for each person, the prior for that is typically in IRT we'd say this was normal. This is decat, categorical. It's one trial multinomial. And the probability is given by eta, that's that mixing constant. And we have 1 through C constants. Now the question is, what's the prior distribution for eta? And this is where we get the Dirichlet distribution. So the Dirichlet distribution right here. There. The Dirichlet distribution is a great distribution. It's somewhat thought of as a multivariate beta, but it basically gives you a set of probable numbers between 0 and 1 that add up to 1, which is really convenient for multinomial data. In fact, it becomes a conjugate prior for multinomial data, which is great if you think about it. Right, so what is this right here? This is what's called a simplex. By the way, I have a great grad school story about that. I was in an optimization class in the stat department. It was a lecture, and the teacher was talking about simplex, and it was a big class, and I was like, what is a simplex? You need to define it. And everybody got quiet, and the teacher laughed, and everyone laughed. And I said, no, I'm not joking. What is a simplex? And then they're like, no, anyway, I hadn't taken a class where simplex is there. Anyway, Ben, what's a simplex?
No idea.
Okay, good.
I did theoretical mathematics.
I believe it is essentially a confined space, right? But anyone else have a definition of a simplex? Hey Siri, define simplex. Look at the way the Dirichlet works for a conjugate prior. This is trying to update as a conjugate prior. Well, if we only had was a one item multinomial, and we were trying to estimate the probabilities for each of those, for people with data in each of the classes and put a Dirichlet on it, then what we could show is that Dirichlet would effectively give us the count of people. The posterior for Dirichlet is the count of people with a response in each of the categories, plus the number that you give for each of the alphas. So think of it this way. If I had a 3-category item, and I had 20 people in each category, right? And we were trying to estimate the probabilities, right? It'd be 0.33, 0.33, and 0.33, roughly. I mean, they're supposed to sum to 1, but you know, there's extra thing there. What the Dirichlet would try to do is basically say, if I give it, I have to give, if I say this is a multinomial and I give it a, I have to give it a character of alphas, what it will do if I give it ones, the Bayesian update step will basically say, this is the number of people I have in each of my categories, and then when it normalizes that, it'll give me the probability. So what numbers you put into this for that vector of alphas, this is sort of the certainty, the relative certainty to what you want the probabilities to be in each of the cases. If you are okay, so 1, 1, 1 in this case would give you a very uncertain amount of weight to each of those probabilities, which is really what we want to have in an exploratory mixture model. We don't want to put weight in each of the classes. It could be the case that you really think people should be in class 2, so you might put 101 here, right? Which would then turn this to 121, and now you can think what the proportions would look like. Right? So Dirichlet, in some respects, is really complicated. It's got all these distributions that form the PDF. But when you phrase it with the multinomial variable, the posterior distribution effectively takes the input numbers and adds to it the observation in each of those cases. And when you normalize it, when you go make this sum to 1, you get the probabilities for each of the cases. Does that sound cool? So Dirichlet is a great distribution. That's why you hear people say it. By the way, in my head, I read it as Dirichlet. In the JAGS code, I have to pull. I really have to show you the manual because this is pretty funny. So you could say, you could phrase it as D Dirch, or Dirch, where it really should be Dirichlet, right? Dirichlet. But it says the name D Dirch is due to a historical misspelling in Winbugs.
So they just stuck with it, they didn't change it.
The distribution was renamed Dirich in OpenBugs, and so this alias is also carried forward in JAGS. But this is where you were asking about compatibility, backwards compatibility of JAGS with bugs. Just so you could do it, you could misspell, make it D-Dirch. But so I'm going to input a vector of 1s for my alpha parameters of the Dirichlet. So here, each person has a categorical multinomial distribution. The probabilities are given by eta. Now I need a prior for eta. Eta is Dirichlet. And then I have to input alpha, so I'm just going to give it a vector of 1s to try to not put any undue weight on my probabilities. Boom. Finally, the last bit of information is I'm going to put a beta distribution on my class-specific item difficulty, because they're probabilities, and I'm going to give it a 1 and a 1 to make it uniform. Yeah.
The comment above it is a typo.
Yeah.
Factor variances.
Yeah, I copied and pasted. Yeah, I'm lazy.
Like, I didn't think there were factors in this story. Maybe I missed it.
Here, the class is is functioning in a role as a factor would.
Those are items.
That's right. And then here are my parameters. And now we're going to let this run a little bit. It's going to take a little time. So in the end point of this, you're going to find that these things are just ridiculously impossible to make work sometimes, particularly in this exploratory case. There are, Ariel.
Keep going. I will ask you a question, but keep going.
So this is a very simple case where I just took the probability of each item. There are other cases in psychometrics that show up, for instance, mixtures of IRT models. One that was really big, probably still is mostly big, but Jorgen Ross, 1990, had a mixture of Roche models, because why not? I don't know that Roche would find that good, because it actually violates specific objectivity. So therefore the mixture really should, maybe there's, within class it's golden, but together it's just, I don't know what Roche would say, I don't know what the Roches would say about that. But I did a study with a postdoc at Georgia, because she brought me this result. She said, hey, look, I took these data from Florida, the FCAT, this is integrated data, and I fit a mixture Roche model to it, and I got 3 classes. And when I'm going to interpret these classes, so in each class had a different item difficulty per parameter, right? Item Roche difficulty, right? I think of this as each class is a different response strategy, a response style, I guess. Multiple strategies. And I'm like, no, I don't think that. And so we did some digging in the technical manual, and sure enough, the FCAT data was, the data we had, was said that it was calibrated using a 3-parameter logistic model. So we were violating the 1-class model with that. This is a Journal of Educational Measurement paper. I think there's been like 2 citations of it. So that's how really popular this is. But they were probably both my mom. But anyway.
I don't know your mom was an academic?
Yeah, well, no. Put blog posts and Google Scholars like, oh, look at that. Anyway. She tweeted about it, I think. I showed my mom the Twitter, and she loves Twitter. She's in her 70s, but loves Twitter. That's like how she gets her news. Sorry, sounds like our president. Loves Twitter. Not quite as many followers. Long story short, the 1-class model was violated. So we came up with a simulation. We said, what happens in a mixture Roche model? I think I mentioned this before. May have mentioned this class. If I did, I'm sorry. But we said like a 30-item test. How many of the items need to have a different discrimination parameter to trigger another class to be mistakenly pulled out by it? And wouldn't you believe it was 1 item? You could have multiple classes in a mixture Roche model if 1 item didn't follow a Roche model from a 1-class design. The other cool thing about this is we kind of took the 3-class mixture Roche model and marginalized across class. And what you would see in this paper, actually I can pull up the paper real quick. What was her last name? See if I can find it real quick. There it is. Spurious latent classes in mixture Roche model. What we could show at the end of this paper was really kind of cool. If you marginalize across the class, what you end up getting, here we go. Here's our data. If you marginalize across the class, right here, these are the class lines. They start to look like a 2PL model, right? So the 2PL is here, and here is the 2-class. Anyway, this is basically, the more classes we add for a single item, we marginalize across it, the ICC we got would start to look more and more like the data we had. There's 2 parts of that make it interesting. You can hijack these models to basically say, you know what, I know my model doesn't fit my data, but if I throw multiple classes at it, and and I don't care about who's in the classes, I can marginalize across the classes, and what I end up getting is a semi-parametric method to do combining a model that's parametric across semi-parametric classes. And that's where you end up seeing another part of psychometrics, which is sort of the semi-parametric structural equation modeling world. You throw a ton of classes at a problem, basically to try to find some type of relationship that's not guaranteed. In our case, it was item characteristic curve throwing at data. If we took that curvilinear regression model and fit class variables in it, we could try to approximate the curve with a marginalized model. Now, it would be very hard, but you can think about different classes of people having different linear slopes. And then when we aggregate across the class, it starts to look curvilinear. So that's another part where this works. It's semi-parametric, yes?
You can finish your word.
Oh, no, it's okay. Semi-parametric is what I was saying.
So if we can get, if in our data set there are multiple data classes, can we detect that using this?
Yeah, and actually there are a number of papers to try to do this too. Former colleague of mine at Georgia, I think her PhD in Maryland was about using a mixture model, I think it's Roche, to detect item parameter diff. So you fit 2 classes, and you find, of course, different difficulty parameters, and you have to try to see if that was actually diff. try to relate that to other things. So the irony is, though, what's funny about that is you'll see people fit in mixture models to fit the data, and then they'll take the result and use, like, let's say they're worried about diff based on sex of a person, right? Male versus female. They'll fit a mixture model to an item, say there's two groups of people, and try to use sex then to predict who's in each group, rather than using sex to predict the data first. So the problem in using mixtures to look for diff is it's subject to model misfit. Guess what happens? I talked about misfit in a simulation where we had a unit dimensional model, we were just off on ICC. Imagine the typical misfit we see in IRT. If you have a lot of local independence violations, maybe the data are multidimensional, but if it's unidimensional, the mixture model is going to pick up on that and think there's a lot more diff than there really is. So it's a very interesting, it could do that. You have to make sure the model fits. Really have to do a good job making sure the model fits. Should we look at our results? Let's look at convergence. Dun, dun, dun. What is happening with our parameters?
Label switching for 1,000.
Oh, so this is the part where I'm going to diverge from the textbook. And the textbook said, oh, the problems in mixtures are sort of what we have in the problems of factor analysis, is that there's some indeterminacy, the directional indeterminacy that we saw before. Yes, that's true. For instance, we're fitting multiple chains. It's possibly the case that each chain, class 1 gets relabeled as class 2, and the parameters have another shift. There's another problem in mixture models. I'll get to that in just a minute. But let's investigate this just slightly, a little bit more. Let's look at the deviance. In our factor analysis, when we said, oh, look at this, we're having this non-convergence, when we looked at deviance, the line was all the same. In a mixture model, if we were doing this as an optimization with a likelihood function, the mixture model does not have a smooth function. It's multiple peaked, multimodal likelihood. And so when we're randomly starting places with multiple chains, what we end up with is parameter convergence that goes to a peak that's close to it, right? It sort of gets sucked into where that peak is. And based on the tuning of the algorithm, it can't get back out. So it gets sucked into one of the modes. Sorry, this is if you think of a likelihood as a mountain range, it's like multiple peaks, right? Some of the peaks are higher, that would be multiple, like what we want to be in an ML solution. Some of the peaks are in different places. But our Bayes algorithm here doesn't have big enough jumps to be able to get out of modes. That brings up a couple questions. Number one, when we want to get out of modes, because in an ML sense, we want the peak. We want the lowest deviance. And the other question would be, so there's sort of a debate. Anyway, point is, you can follow, the textbook says, oh, this problem right here, this isn't it. We should see that if we read the textbook exactly, which said the problem is this indeterminacy like in factor analysis, we would see one deviance because there's one mode to that. But no, there's multiple problems with this. There's multiple modes in the analysis. So
Local maxima?
Local maxima, that's right. In the mixture model and a cluster analysis, many of you have done k-means. Ever seen that before?
Well, that was going to be my question. How they related to K-modes?
K-means?
Oh, K-modes.
K-modes.
Yeah, it's a strategy for dichotomous data being used that is a spin of K-means, but for binary data they call it K-modes.
Same thing, same issue. K-means have a problem. K-means is another cluster analysis. You say I have K clusters.
Yeah.
And often you assign to a person to a cluster based on how far their distance of their data is in a multivariate sense, the mean of each cluster. Perhaps it'd be the mode in the case of binary data. But you're assigning people to, the algorithm in each step is assigning people with certainty to each. Whereas in this mixture model, we're not. I guess in each iteration, everybody has a class. Anyway, it is related, but it's not. The result of the mixture model is that at the end, people have a probability of being in each class. The result of the k-means, yes, I guess you could go and look at where the closest is and try to use an integral, multivariate integral to get probabilities, but
It's more deterministic.
it was, yeah, in the way that it works. So we can't simply flip the sign of the parameters, is what I'm going with this. The book advises one thing we can do, and this is what M plus started doing, by the way. M plus, way back in the day, just let us have the output as is. Like, oh, and you would see, you'd run an analysis, M plus would randomly start in different places, and if you ran 2 different analyses, you could have the case where you'd have the same set of probabilities for the mixture probabilities, but they'd be reordered. Right? So the one for class 2 looked like class 3 over here, and sure enough, when you looked at the parameters for class 2, all those were the now parameters in class 3. That's what we call label switching, right? In our case, constraining label switching only can do so much because we have those multiple modes. One of the constraints for label switching that you can do, get down to where it is to order the probabilities of the classes. And those ordered probabilities are right here. I'm going to draw an eta star from a Dirichlet. That's the probabilities. And then I'm going to go sort those. It's a kludgy way of doing things, but if I ran this instead, which will take a while, you see there's only so much we can do, and when I plot out the deviance, we're still going to have big chunks. So, what do you think? All right, question for you. Are multiple modes a feature or a bug? I don't have an answer to this, by the way.
Can you elaborate?
Yeah.
So in a lot of, when you look at papers in the Bayesian world, when they talk about samplers, like Stan versus Jags, one of the problems that Stan paints, the people who built Stan paint, not just Stan, other algorithms, paint the Metropolis version that we have here with the tuning it's done, is that once you get stuck in a mode, you can't get back out of it. And the question would be, what's appropriate? Right? That's arguing, saying the multiple modes are just the feature of the data. You need to sample from all the modes to get a sense of what your posterior looks like. The idea being that the likelihood function is just a non-normalized posterior distribution in this case. And so if the likelihood is multimodal, you'd want to sample from all the modes to get a good sense of the posterior distribution, including the modes as well. That would be multimodality is a feature. The ML sense, if the reason why an ML algorithm, like an M plus, randomly starts a multiple number of times and runs the convergence is because the optimizer they're using finds the peak that's closest to the starting point. And you want to keep seeing where the peak is because unless you're at the maximum of that, then the ML properties don't apply. Right? So to the ML algorithm, you call that a bug. What do you think? Feature or bug? If it's a bug, in theory, we could find the chain that had the lowest deviance, pull those parameters out, and report them. If it's feature, we'd want to look at across all chains and look at the multimodality. I don't know a good answer to this. My mind is still stuck. I fit too many mixture models in the ML sense where I want that highest deviance. But a lot of the arguments, again, these arguments are sort of straw person arguments about why the estimator that you see in JAGs isn't sufficient is because within a chain, it's not, when it's tuning, it's not allowing us to get farther outside of the mode that we're in. And then if you switch to an algorithm such as Stan, which by the way, you wouldn't be able to have the categories involved, you'd have to marginalize across it because it doesn't have categorical latent variables in it. Because of that, Stan can jump easier from mode to mode where things go.
I think it depends on how those nodes are coming about. Like with CFA and IRT and stuff, like I don't want 2 modes. That's just a trick of algebra.
Right.
And it's a lack of orientation. So to fix an orientation that makes sense, philosophically. But that's not always the case, right? And more complicated likelihood functions, right? You could have multiple nodes that are appearing that are not specifically algebra.
Right, exactly. And I think that's the question I have. Part of this is label switching. but we're going to constrain it, and if it does run by the end of class, we're going to end up having modes. We're going to see the modes themselves. Here, you know what I'm going to do? I'm going to grab the HTML file for this, and we'll just look at that.
Can I ask a question?
Yes. Yes.
The part that I think is traveling mentally is where the information that we might know about the data simulation process or behind all of that come to play a role. Because asking the question about the mods, I keep going back one, what we should expect given how the instrument have been developed or how the data have been generated. It is fully exploratory. Do we have any theory to that?
I don't know that there are. I don't know that you would even say that about mode. I guess you could say lock into one mode because if you go and look at a mode's data, this counter to what I thought with theory. Is that what you're saying? Like, oh, we shouldn't see probabilities look like this because it's not a valid node or something like that. What you're trying to say. I guess you could say that. I think we'd want to express that prior somewhere, if possible. Or another version of these, you can put constraints on this. You can make this is sort of the EFA version of factor analysis. We can turn this into the CFA. By the way, we have a whole course on that next semester I'm teaching. We sort of have the diagnostic models version. But sorry, keep plugging my classes. Don't forget these two courses either. So it's tough to decide. I think that's the part where I'm at in a Bayes sense. But let me just.
So that's why I'm going to use cross-validation, because if you pick the highest global maximum using some algorithm, you maybe come across with the overfitting problem.
If you have just too much parameters in your data, you may be honing in on features of this data set. Exactly. Mm-hmm.
So if you prediction error to see if it's reasonable to pick the to find the highest mode.
Mm-hmm.
Yeah.
Possibly. Let me just show you what happens with the modes again. Get all the numbers out. Here's a better view of the deviance for this. Right? There's clearly a mode here. And so I went to go, okay, let's think of it as a bug. Let's go and look for the lowest deviance. So this pile of caterpillar deviance right here, 3 of the chains are down here. Right? 1 of the chains up here. Now I don't know if I deleted this or not. We look at these chains. I pulled out the 3 chains. This is actually chains 1, 2, and 3 if you investigate it. And I went and looked at the convergence. Has it converged? That's our Gelman and Rubin. No. Turns out there's yet another mode buried underneath those 3. Right? There may even be 2. There might be 3 separate modes to it. Right?
Is this a problem that's always in mixture models? Does it show up in any other type of model?
It shows up in other types of models that aren't likelihoods that were smooth. And so what do I mean by that? Technically speaking, 3PL it could show up in. There's a class of models that follow, if you have a posterior that's roughly exponential family, right? If you have so normal data, normal error, normal factor, posterior is going to be normal. Not going to see this, all right? A lot of IRT, probably not going to see it. I think it's still, you can say it's a exponential family, potentially, most of it. But most of the models we're going to talk about in psychometrics, you don't see this in. It's when you're coming up with new models, or if you have a mixture prior. Now, there's nothing that stops us from putting a mixture model on a prior distribution. For instance, if you want to do an EFA, and you set up the model so that each loading has a probability of being exactly 0, or some other value. That's a model we could fit with this. But now we have a place where we have a mixture prior, which means we may end up being in the spot where we see this as well. Most of the times where you see this in psychometrics, it's mixture-based models.
So what makes 3PL different then?
3PL, because that C parameter's out in front, doesn't follow like the exponential family anymore. It gets outside of that, and then you're not guaranteed for that convex likelihood. Although the times I've done it, again, I'm not a 3PL aficionado, but I haven't seen multiple modes in it. Probably because the beta we put on for the prior smushes all those into something that would be a little bit more recognizable. Yeah.
So we are talking about the multiple modality.
Yes.
The joint posterior, right?
That's right.
Not each of the posterior, marginal posterior.
That's right. This is the joint posterior. Yes. The marginal posterior also has multiple modes, but in the joint posterior, we have that same problem still expresses itself.
But each of the actually parameter, it should have just one people. No, I mean joint posterior maybe it might have
Well, the joint posterior will clearly have it. The marginal actually has multiple as well. So the optimizer that you'll see in other methods, M plus will iterate between EM, which is a marginal, and quasi-Newton, which is not marginal. The quasi-Newton itself will also have multiple modes in a marginal sense. Yeah, it's a good question though. It is, and I don't know that they're guaranteed to be the same. I haven't thought that much. It's a very good question to ask. I like that question. Very complex, but it's hard to tell what's going on. So what I did by the end of this is I just gave up. And you may think that's a cop-out, but here's my posterior distribution by parameters.
That'll go into my homework. By the end of this, I just gave up.
So if you believe it's a feature, this is what you're going to say about each of your probabilities. Here are my probabilities. Right, I could make this is a density plot breaking them down by chain, but you could go and put this into a single chain. So how would you summarize the probabilities of being in each class?
That's my thesis statement.
The other thing is you would want to also describe what each class means for probability. Oftentimes we take the mean of each probability for item difficulty and go and say, oh, look, this is the easy class, or these are hard. That's almost impossible to do with this data too when they're multimodal. Look at so here, the probability of the average probability across all of the chains of getting the first item right for people in the first class is 0.439. The standard deviation of that is 0.416.
The number line.
I didn't know that was possible. Yeah, somewhere in there that person exists.
From here to here, you may get a guy.
Now, there are people who do mixtures and only use Bayes. In fact, Al Cohen, good mentor, colleague, friend, think really highly of him. I almost consulted him and said, how do you keep this from happening? Because there are people who've done this for many years in WinOaks or in JAGs, and you can go look up their stuff, and there's probably better ways of doing it. I just decided at this point, these models are so ridiculous, I don't even want to go and pitch this to you because I don't believe in the exploratory mixture. Let me see if I can find it. Lisa and I were on a committee of a student at Kansas last year. Yeah, let's see if I can find it at the library. Probably not. Anyway, she did a semi-parametric structural equation model where in the mixture itself, she was trying to see non-linear relationships between like a path model, and so she used this to go marginalize across the classes. That's where I like using it, or putting more constraint on the classes to know what they really mean. Turns out when you start to constrain the classes, you start to cut down on the modes and the data themselves. Another student at Kansas that Lisa supported, Lisa was her advisor.
No. Luke? No?
Hongling.
Oh, another one. Okay. Changing topics.
The multimodality.
Yeah.
Anyway. One thing we could do is the thing about it is we really need to check model fit. I have another posterior predictive check here at the end. And this was the covariance between items 1 and 2. One thing I wanted to note, here are all the flagged covariances again. You'll note this model, the mixture model, has a really hard time. Where the misfit's happening is that data observed covariances are much higher. There's nothing that's below. Right, the model has a really hard time getting big enough to go and get the covariance. Right, so we're sort of under predicting the relationship between variables based on this model.
We've seen that in a lot of our models, actually. We tend to be biased downwards.
It's tough. I would say the CFA and the IRT, it never had this much though.
Sure.
Right? Here's one where it's too low. But yeah, I would say that it's small samples. I don't, yeah.
Well, this model has like no variability in it. Everybody in each class is supposed to be exactly the same,
That's right.
and that's just not real.
Homogeneity within class, exactly. So what do you think of these models? Gonna run out and do mixtures now? Some of you are already doing them, right? But
I actually have a question. The reason I thought I asked there possibly should be one really high peak for the marginal distribution of each parameters was otherwise how do we decide the parameter estimates?
right.
Is it mode or median or EAP? What?
Right. No, there's no easy way to do it. The really high peak, if you have a really high peak, you'd think MAP would be that's the modal one to look at, but there's no easy way to do. The other thing I will also note, just in general, thinking about when you fit this with M plus, or the marginal maximum likelihood algorithm, the number of modes in the marginal distribution tends to be higher the more the number of classes show up, right? The bigger the number of parameters, the more modes show up. M plus will try the algorithm 20 times at random and try to run it through to the end on, I don't remember where they're starting it now, so I don't even want to say that. But basically they try a set of random starts and then they pick the highest values, run those to the end, and they tell you if they never found the same highest likelihood mode. So they warn you, hey, these results are maybe unstable.
You could mix the posteriors then.
Oh, yes, you could. That's what this plot right here is trying to do with the item parameters at the end. Or actually, these are the etas. Like how do you report it? You pick the mode, right? Because the mode would be here, 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 right? But those probabilities won't sum to 1.
Yeah, so you mix them based on some criteria, right? And
Yeah.
you normalize.
Yeah, so I'm on the camp of this is a bug, not a feature, but
I mean,
if you need to create a new algorithm to sample from multiple modes, you'd say this is
it's not helpful, certainly.
So, any other thoughts? All right, I'm done. 20 minutes early. That's a little bit early, right? Does that work? All right. I'll stop here. If you have questions after class, let me know. Thanks. Have a good weekend. One last class. Again, we're having a team taught last class. Lisa is going to teach us all about models and stuff. Did I just kill OBS? There it is. All right. See you later, everybody.